So I want to consider a curve that looks like this. Now, I'm going to show you that if the ratio of distance between an arbitrary point in the origin to the distance between it and some fixed vertical line I call directrix is a constant, then this curve is going to represent one of our three conic sections with f as its focal point if it's a parabola, or one of its foci if it's an ellipse or hyperbola. So I'm going to make the assumption that the ratio of the distance between my arbitrary point P on the curve and the focal point to the distance of point P and the directrix is merely a constant I call E for eccentricity. You'll see why I want to give it a name in a moment. So let's see when I rewrite this equation. I think distance between P and F is my radial distance from the origin for P. Now the distance between P and A, this distance right here, if you slide it down, isn't that this total distance of B minus the length of the horizontal leg of that triangle? So that would be the full length B minus the length of the horizontal leg. Let me get rid of fractions. Let me write in terms of x and y. That's just x. Let me square both sides to clean it up. Let me bring all the terms involved in the variable to one side. Did I square properly? My goodness. Squaring both sides, I didn't finish. This squared got it. Minus twice the product of those two, I like it. But doesn't it give me this? And bring in all the x squared, or all the variable terms to one side. Keep the constants to the right. Now I like to come in and complete the square on x, but I've got a coefficient I don't like in front of x squared. So let me do this. Shoot. I'm stalling because I don't like the board space that I have. How about this? Now let me complete the square on x. And compensate. Now certainly on the left-hand side of the equal sign, when you look at the first three terms, by construction, that is a triangle that is indeed equivalent to a perfect binomial square. Now on the right-hand side, looks like I've got a single fraction whose numerator is this. Now these two terms completely cancel, and my numerator is nothing more than e squared d squared. And finally, if I put this in standard form, dividing both sides by this to force it to be a 1, so that can be this. All right, I have to admit, I'm writing too small. So let me go ahead one more time, jump to the top, give myself more clean room. Okay, much better. Now, like I just said, forcing this to be 1 and seeing if I come up with an equation in the standard form of my conic sections. So dividing both sides of that beast, I'm left with this. All right, everybody, here I go. Now I have to confess, if E is equal to 1, I think so much what I have in this equation is completely horribly undefined. But if the ratio of this distance is equal to 1, does not mean by definition I've got a collection of points equidistant from a fixed point F foci and a fixed line called a directrix. That's my definition of a parabola. So I know if E is equal to 1, I got a parabola. That's for free. Now, notice what happens if E is less than 1. Then this thing's positive. All the other squares are positive. Therefore, I got an ellipse. And if E is bigger than 1, that denominator is always positive. But if E is bigger than 1, this becomes negative, and I got a hyperbola. So how about if I say it this way? Consider an equation of this form or this form. There's 4 different forms. The polar graph of each of these is a conic section. And in particular, if E is less than 1, equal to 1, or bigger than 1, I have an ellipse, a parabola, or a hyperbola, respectively. So I've just proven that an equation of one of these 4 forms gives me one of those conic sections. Now let's see how we can put this to practice with graphing. And you will be just so impressed, if you're not already, from trigonometry, and how easy it is to sketch these polar graphic conics. It will be mindless.